Bismillahirrahmanirrahim. Assalamu alaikum. My name is Umar Daraz Ghori from Dawood University of Engineering and Technology. My topic is temperature dependent term by Arrhenius law activation of energy. So temperature dependent term Arrhenius law for many reactions and particularly elementary reactions, the rate expressed can be written as a product of temperature dependent term and composition dependent terms. If we see in the next equation, R1 is equal to F1 temperature, mean R1 the temperature, R1 the function of temperature and composition. For such reaction temperature dependent term, the reaction rate constant has been found in particle cases to be well represented by Arrhenius law. This equation K is equal to K naught E minus E by RT. This is show the Arrhenius equation. Rate of reaction is a function of temperature and composition. Take above rate constant not rate and K depends on temperature, while rate K depends on temperature, mean its rate constant depends on temperature, while rate of reaction does not depends on the temperature. A rate constant change the rate law. So what's the factor involved in this equation? K naught is the frequency factor or pre-exponential factor, while E is showing the activation energy. We can also write about instead of it EA, or we can also write E. Both are the same. So R is the general gas constant, while T is the temperature. In the rate of reaction, it depends on the two things. One is temperature, other is composition. If reduce concentration of rate of reaction, it will reduce because it does not affect on rate constant. So where K naught is called a frequency of free exponential, as it is the explanation of the previous equation as I have told you. So forward to the next. At the same concentration but at two different temperature, Arrhenius law indicate that ln R2 divided R1 equal to ln K2 by K1 equal to activation energy divided R, or this the for two temperature 1 by T1 minus 1 by T2. Prove that E is constant. Derivation, let's check how this equation will be formed. R1 equal to F1 temperature, function of temperature and composition. So if we check it on concentration constant, so del C will be equal to 0, because we are talking about that at time from T0 to T1, so there is no change in the concentration. That's why we take it 0. Then the equation will become like R is equal to K, mean rate of reaction is equal to K, or so K is equal to, as we have seen in the previous equation, K is equal to K naught E minus E by RT. This is the Arrhenius equation. So if we integrate both the sides, it will equal to ln R equal to ln K equal to ln K naught EA by RT. So exponential finish with log. What will we will get the above equation. Now integrate the equation on the both sides, so we will get the final result as mentioned in this ln R2 by R1, like this. This is the derivation of the previous equation. Let me show. This is the final equations. Now we will move toward graphical representation to show temperature dependent terms Vs rate constant. What's the relationships of temperature and rate constants? First move toward the graph. According to Arrhenius approximation, at y-axis there will be k, mean rate constant, while x-axis there will be T, mean temperature. It's not T, it is 1 upon T. Slope is E by R, mean activation energy divided rate constant. If we see from the axis of straight line of equation, so EA by R is M, while 1 by T is X, and ln A is B, mean constant, and ln K is y term, which we draw the equation for a straight line. If we have a rate constant and a temperature value, then we can easily find the activation energy. In graph, T increase from left to right because it is 1 upon T, not T. K increase in the upside by floating of K, and 1 upon T we will get intercept. Activation energy will be maximum where temperature maximum, and activation energy is a barrier in a reaction to happen. If how many temperature increase in that quantity, we need activation energy to break bond. At top, activation energy maximum, if it concentration come toward down, so activation energy will be decreased. In this graph, one slope is inclined while second one is steep, and in steep slope one changes of activation energy is high. Its value of rate constant change quickly. Where activation energy high, it means that reaction is more temperature sensitive. If temperature is present, then it will proceed, otherwise not. In inclined slope we change temperature, but a little change in rate constant K. That's why it's not steep slope. Energy changes is higher in steep graph as compared to inclined slope. Now let's move toward theory of these graphs. So temperature dependency of reaction is determined by activation energy and temperature level of the reaction as illustrated in figure 2.2 and table 2.1. These findings are summarized as follow. From Arrhenius law, a float of lnVs 1 upon time the straight line, which large slope of E and small slope from small e. The steep line has a higher activation energy, while inclined slope has a lower activation energy. The next point, reaction with higher activation energy are very sensitive, with low activation energy are relatively temperature insensitive. Reaction are more sensitive at low temperature. At any given reaction is more temperature sensitive at a low temperature than at a higher temperature. From the Arrhenius law, the value of frequency factor can or does not affect the temperature sensitive, because can or does not affect by temperature. Let's move toward forward. Temperature rise needed to double the rate of reaction. It means that we need to rise the temperature to double the rate of reaction for activation energy and average temperature shown. This is the temperature and active energy data. That's enough.